Okay, so in this lecture we are going to study quasi-periodic motion or quasi-periodicity. Now we know how motion looks like when the attractor is a point. If this is your phase space, the trajectory slowly winds down to fixed point. Now, the example could be the damped pendulum or any of those, any sort of a motion, for example, damped oscillator. Here's the equation. Or I can have some other, doesn't really matter, but some sort of a motion which has damping in it. So this is your conventional damped oscillator. And that yields a stable solution where the trajectory comes to a fixed point. The attractor is a fixed point. Or the other case could be, let's say these are the coordinates of the phase space. It could be that the trajectory is attracted towards a limit cycle. It is ramping up the motion here, or any motion outside of the limit cycle spirals inside, and this is my attractor. So what should be an example of such a motion? Well, the example can be something called as a oscillator where the damping depends upon this guy. So if you notice, assuming x is less than 1, I'll have the negative damping. In other words, I'm going to be amping up the amplitude so that it hits this attractor, and for modulus of x greater than 1, I get the positive damping. So this is going to ramp up the amplitude, increase the amplitude, and this is going to decrease the amplitude. And of course, we've also studied the chaotic attractors. Third is the chaotic attractors, and so I'll just label fixed point attractors, limit cycles, and I have the chaotic attractors like the Lorentz attractor, or we also saw chaotic attractors in terms of discrete dynamics like the logistic map had chaotic attractors as well. So, by the way, one more thing is that how should the motion on a limit cycle look like? It is closed, and as you can see, it will keep on going around the cycle, so it is periodic. It is bounded, it's closed, the orbit is closed, and it's periodic. In contrast, the chaotic attractors are bounded and aperiodic. And not only that, as we have seen, they depend sensitively on initial conditions as captured by the Lyapunov exponents. So it turns out that in this lecture, we are going to be interested in quasi-periodic motion. Fourth kind of thing, other than the stable fixed point, the limit cycle, periodic motion, or the chaotic attractors, the quasi-periodic motion. So in order to study this, let's consider first a periodic signal. What is a quasi-periodic motion? Quasi-periodicity. So let's say a periodic signal, and periodic signal has a period t. So after every capital T time, this recurs, and let me find the Fourier transform of the signal. Now, as we shall see, you can put it in MATLAB or anything. The Fourier transform of a periodic signal would consider peaks at all the multiples of the fundamental frequency. So this is how, if I have a fundamental frequency, I'll have delta function peaks at, they don't have to be equal in size. I'll have delta function peaks at all the fundamental frequencies. Now, a quasi-periodic signal can be regarded as a signal which is a mixture of not one but many fundamental frequencies. Or you can say that it is a signal which has got many periods. It's not a periodic signal, but so for example, if I have a signal which I parameterize by variables, then it is periodic in each of these variables. So for example, it would be some ti plus ti, ti plus 1, tn. This is going to be equals to gt1, t2, ti plus 1. So it's periodic in each of these variables with fundamental frequencies given by related to the periods. So that is the first condition. The second condition is that all these frequencies are incommensurate. What does it mean? Well, when I say the frequencies are incommensurate, what I really mean is that a relation of the form does not hold for any set of integers m1, m2, mn. I'll put that as a capital N. So if I have a set of frequencies omega 1, omega 2, omega n, such that such a relation does not hold for any set of integers, capital N integers, then I have what I call as this n frequency quasi-periodicity. So you can take the entire signal to be a mixture of all these fundamental frequencies, such that this relation is satisfied. There is a separate period for each of these variables, but the combined signal as a whole would not be periodic. And moreover, the n frequencies representing the signal would be related by such a relation, that such a relation would not exist other than, of course, the trivial case where m1 equals to m2 equals to m of n equals to 0. That's the trivial case. So this type of a motion, which is a mixture of many fundamental frequencies that are incommensurate with each other, is called as the quasi-periodic motion. So, as we have seen, one of the hallmarks is that the all n frequencies are incommensurate with each other, or in other words, in terms of the Fourier transform, I'll get the Fourier transform would be consisting of all integer linear combination of the fundamental frequencies. So I'll have some all integer linear combinations of fundamental frequencies. Now, visualizing the quasi-periodic motion. How does one visualize such a motion? And we'll go into some very interesting geometrical aspects of these incommensurate frequencies. I think it will be better to consider a two-frequency quasi-periodic motion. I can represent the two-frequency quasi-periodic motion by two variables, theta 1 and theta 2, and they do their own thing. And certainly I can represent like modulo 2 pi these two angles, because they wrap around the circle after 2 pi degrees. So notice that if I specify one angle, Then I have a motion on a circle. I've got one angle, one frequency, and I have a motion on a circle. What is the geometry associated with specification of two angles? Think about it. What geometry comes into mind? I have got two angles. The natural thing is to consider a toroidal surface. I've got two frequencies, two angles, and if I can draw it properly, this is one of the angles around this orbit, theta 1, and then I have the motion on the surface of this toroid given by some angle theta 2. So now I think the quasi-periodic motion would be clear. What's happening is that these two angles are doing their own thing, and there is a motion across theta 2 and there is a motion across theta 1 over the surface of the donut, and their trajectory is going to wrap around and go around the surface of the torus. Now you can tell me, what does incommensurate mean? So if omega 1 and omega 2 are incommensurate, what happens? So that means I do not have such a condition. I do not have unless both m1 and m2 are 0. So what does that mean? Well, I can define a rotation number r as the ratio of the fastest frequency to the slower frequency. This is my rotation number. So when I say omega 1 and omega 2 are incommensurate, when r is an irrational number. That means it cannot be expressed as two integers, m1 divided by m2. So what does that mean? That means that, just think about it, if r is an irrational number, as time goes on, the orbit keeps going on the... So first we can consider what happens when r is an integer. That means I can find m1 and m2 as integers. What happens when the rotation number is an integer? So think about it. As time goes on, let's say if r is an integer, or a rational number, as time goes on, we are going to get closed orbits. Think about it. I have this torus and I have got this r captured by this guy, omega 1 plus omega 2. And that turns out to be an integer or a rational number. So let's say omega 1 was 3, omega 2 was 2. Eventually, what will happen is, after this is 1. So For every 3 of these rotations, I get R2 as 2. It rotates around twice. So something like that. 1, 2, 3. I'm not doing it very nicely. So this was, let's say for a simple reason, this is 1 for simplicity. So after 3 windings across, the orbit is going to close. So I am going to draw it again. Yeah. So drawing the case where R1 is 3 and R2 is 1. So it takes some wrapping around. It goes over the torus, comes underneath. It goes again over the torus, goes underneath. It goes again over the torus, goes underneath. So after 3 rotations, R2 wraps around the whole thing and the orbit closes it on itself. What happens when R1 is 3 and R2 is 2? Well, we are at least certain that after 6 R1 rotations across R1, or I should say, this should be omega 1 and omega 2. After 6 wrap arounds on the theta 1 direction, I'm sure to close the orbit again. That is because 3 and 2 have no common factor. So the orbit I am at least guaranteed to close it around after 6 of them. So it would take 1, 2, 3, 4, 5, 6. By the time 6, I would have gone this way twice, and the orbit is finally going to close it on itself. So as long as omega 1 by omega 2 is a rational number, I'm guaranteed that I'm going to wrap around the torus on closed orbits. What happens when omega 1, omega 2 is an irrational number, or what I call as incommensurate? So these are closed orbits. This gives me a periodic motion. Well, when this is an irrational number, I'm never going to close it on the orbit. I'm going to keep on wrapping around this torus, but the orbit won't close on ever. So and that is called as quasi-periodicity, where as time goes to infinity, the orbit comes arbitrarily close to each point on the torus. Point on the torus, but doesn't close on each other, and eventually it's going to fill up this whole space rather densely. It's going to come arbitrarily close to each other, each point on this torus. And we won't get either closed orbits or a periodic motion. So this phenomena is called as quasi-periodicity when I have incommensurate frequencies. We saw the example of 2 incommensurate frequencies. In general, if I have n incommensurate frequencies, I'll have an n frequency quasi-periodic orbit. So in other words, when R is irrational, we get trajectories that wrap on the torus without closing. Eventually, the trajectory will come arbitrarily close to each point on the torus. So I guess this distinction of a rational rotation number versus an irrational rotation number is clear. As long as I have a rational rotation number, I can express this in terms of the integers. Let's say I said 3 by 2. So I'm sure that after 6 cycles on this guy, I'm not only going to get, if I have 6 cycles of this guy, then I'm going to have 3 cycles of this guy. So eventually I'm going to land up on the same point. I'm going to go twice around this guy, and I'm going to go 3 times around this guy, and I'm going to eventually come to the same point where I started, and I'll have a closed orbit. So now the question might arise, is there a way to rule out quasi-periodicity? So these are questions for you to think about. Can dissipative maps have quasi-periodicity in general? Or, for example, what happens to volume decreasing maps? And quasi-periodicity. Notice that what is invariant in the quasi-periodic motion? It is the entire motion is on a torus. Entire motion is on a torus, and topologically it won't change. The dynamics is mapping the trajectory on the torus, on the same torus itself. The question is that can that happen in a dissipative map? So these are some questions, interesting questions for you to think about.